This is Unit 3, Video 6. In this unit, which is Part C of the notes, we'll talk about the periodic table, kind of the central document of chemistry. And here you see some old, early chemists trying to figure out what the molecules would look like and put together a little periodic table. Periodic table was put together quite a while ago, or at the beginnings of it, back in the 1800s, and we'll introduce to you how it was put together and why it was put together in that form. Now, the word periodic actually refers to the fact that the elements have similar properties at regular intervals. This means properties repeat. In other words, you can say the properties repeat, or repeating properties. So periodic can be replaced with the word repeating. And you can see here, for example, a graph has been made, and something called first ionization energy is graphed, and you can see the repeating nature of it. It goes up, then it goes down, then it goes up, then it goes down, then it goes up, then it goes down, and this repeating nature is why we call the periodic table periodic. This is just one thing that was graphed. There's a lot of things we can graph about the periodic table. Now, Mr. Mendeleev, Dmitri Mendeleev, was the one that was recognized as the first to put together the periodic table in its modern form. And he is a Russian chemist. There are a few Russian chemists that are featured on the periodic table. And what he did is he arranged the elements by atomic mass. Now, atomic mass is the bottom number on the periodic table. So if you take a look at an element, for example, carbon, which is element number 6, has an atomic mass of 12.01. So he arranged the elements by this mass down here. Now, it turns out that wasn't the perfect arrangement, and there were about 5 elements that had to be flipped, because eventually the elements got arranged by their atomic number. Right now, the elements are actually arranged by the atomic number, which is the number of protons in the nucleus, recall. So he did it by atomic mass, and he also discovered the periodic law. The periodic law is the fact that elements will repeat in their properties every once in a while, and usually every 8th element had a repeating property. And he also predicted undiscovered elements. Now, the way he did this is here, his periodic table actually had holes in it. So after he arranged the periodic table, there were a bunch of holes. So this, for example, element was not there. This element was not there. There's a bunch of elements that weren't there, but he predicted not only those elements would be discovered, but he also predicted the properties of those elements. A good example of this was the element technetium, element 43, which wasn't discovered until a few decades after he predicted it. And by the way, Mendeleev is honored on the periodic table. Element 101 is named Mendeleevian, after Dmitri Mendeleev. Feel free to get yourself a mug, a periodic table mug, just like so. So let's talk about a little bit the properties on the periodic table of the different elements. The first property we'll talk about are the states of the elements. Remember, states are like solid, liquid, and gas. And if you take a look, most of the elements are actually solids. So the yellow here would be solid. And you'll notice that most of the elements on the periodic table are yellow. So solids are the most common on the periodic table. Now, this is at room temperature. Obviously, if you heat them up, they'll melt, so you'll have more liquids, more gases. But we're discussing room temperature, which is 25 degrees Celsius. You'll also notice that there are 2 red elements. Now, these 2 red elements are the famous liquids on the periodic table. They are element number 80, mercury, and 35, bromine. Both of these are liquids. And so the rest, that should be an L for liquid, and the rest of the elements are gases. The gases are actually on the right of the periodic table. Here they are. These are gases. And there's also hydrogen gas. That's on the left of the periodic table. He's very special. But the noble gases, these right here, are all going to be gases. So most of the periodic table is made up of solids. You got 2 liquids, and you got about maybe 12 or so of the gases. 2, 4, 6, 8, 10, 11. And we're thinking that this one here is also gas. Some of these bottom elements have actually been named, and they are currently essentially non-existent in terms of they decay really quickly. So that's why the elements down here in the older periodic tables have no names, but they have been named, and they do have names now. We've talked about metallic character in a previous chapter. We'll repeat it here, And the periodic table can also be broken up into metals and nonmetals. Most of the elements are metals. You'll see that about 75% of the elements are actually metallic. And the nonmetals then will be on the right side of the periodic table. Here are your nonmetals. And so the semi-metals are right in the middle. And that includes boron, includes silicon, germanium, arsenic, antimony, tellurium, polonium, and then astatine is sometimes also included in the semi-metals, also called metalloids. So you can also call these semi-metals. And remember that semi-metals have properties of metals and nonmetals, and that's why they're called semi-metals. On your periodic table, there's a staircase. Remember, the staircase looks like this, and then any element touching the stairs would technically be a semi-metal, except aluminum. Remember, aluminum was the exception. It is a full metal. We also define groups and families. This is another look at it. Remember, we said groups are vertical columns, so this is group 1, and periods are horizontal rows. This is period 5. So an element that exists in group 1 and period 5 would be the element rubidium. And so the group numbers are usually referring to the first two, and then you skip a bunch, and then you go 3, 4, 5, 6, 7, 8. And then what you do is these are actually labeled as B, group B elements. As you'll see, this is group B, and this would be labeled as group A. And so this would also be group A elements. Alright, let's take a look at some of the groups specifically, individually. So the first group we'll look at is the noble gas group. This is the last group on the periodic table. This is group 18, and group 18 elements are very stable. They're called the noble gases because they are unreactive. Noble meaning behaving well, think of it that way. And they are unreactive because they have filled electrons. Their levels are actually full of electrons, so they don't need any more electrons, so they will not be reacting. And all elements actually strive to be like the noble gases, because noble gases have filled electrons, and so every other element will want to have filled electrons, just like the noble gas. Here you have the 5 noble gases: helium, neon, argon, krypton, xenon. You may recognize these as emission tubes. We looked at some of these through spectroscopes. So each one has a different color. And notice that the closer we get this way, the more blue the light becomes. That's because you have more and more energy levels, and you're filling more and more of the electrons. You have more electrons, you have more energy levels, so you're actually becoming more and more like white light as you go down the periodic table. The next group we'll look at is group number 1, and these are called the alkali metals. This is group 1. Now these are soft. They're all metallic. That's why they're called metals. They are soft, low density, which means they float. Many of them float on water, and they're extremely reactive. The word extremely means even if you throw it into water. Here you have one of the elements. This is probably, I'm thinking rubidium, the element rubidium being thrown into water, and it just ignites instantly. They're soft. You can actually cut them with a knife. So here is the element lithium being cut with a knife, regular knife, really soft. And when they react, they form ions with a charge of +1. And we'll see why this is the case a little later. And here it says they are not found free in nature. And the question why is answered by the fact that they are very reactive. The reason for it is they are extremely reactive. That's why they are not found in nature as free. So here are the pictures of the 5 alkali metals we want to look at. This is the first one, lithium. Notice they're floating. Now they're actually not floating in water because they'll be reactive with water. Lithium here is actually floating in mineral oil. This is actually mineral oil, which has a density that's less than water. And so if it's floating in mineral oil, lithium has a really low density. It has a density of about 0.5 grams per mil, which is really low for metals. I mean, half of, much less than water itself. This is the element sodium. Here sodium is actually at the bottom of the same mineral oil. It's a little more dense. Sodium does float in water, however. And here is potassium. This is element number 19, potassium. We have rubidium, and finally we have cesium. Now notice that these are also sealed in glass ampules, and the reason why they're sealed this way is because they are extremely reactive. All of these have to be kept in a special oil or a special glass ampule Otherwise, they'll react even with the air around them, and they'll disintegrate, essentially. Now, here is a famous demonstration of sodium added to water. If you add a little bit of sodium, so this is sodium actually, this would be sodium metal. If you add water to sodium metal, what you'll see is that the water ignites. The reason why it ignites is because sodium metal is able to split water into hydrogen. And hydrogen gas is explosive or flammable. So sodium turns water into hydrogen. That's because water contains hydrogen. And sodium also turns water into what's called a base or an alkali. And that's why sodium is called an alkali metal. Right, group 2 are called alkaline earth metals. Now, these have the same word in them, alkaline, which means they do a similar thing to the first group elements. However, these are harder. You can't really cut them with a kitchen knife. They're denser. They all go to the bottom of water. They don't float. So here you see the element calcium, for example. It went to the bottom. Previously, when we saw the other group element, you actually saw it float at the top, but calcium goes to the bottom. And they're also very reactive. When they react, they will form a +2 ion. So each one of these will, that's why they're in group 2, they will form a +2 ion, which is very nice, very convenient. Here they are. This is the element beryllium. This is magnesium. As we go down, we're going down the periodic table again. And this is, we have strontium, barium, and calcium. So this is calcium, this is strontium, and this here is the element barium. And so some of them, this one looks like it reacted a little bit, but all of them are metallic. You should see a nice luster to them all. They should see shininess. Luster is shiny for the metals. Now, the reactivity of both of these, group 1A and 2A, increases as you go down the group. So the example here is sodium. This would be sodium metal being placed in water, which ignites, notice. And then you put potassium in water, and it ignites even faster. So potassium is actually more reactive. If you take a look, potassium actually sits below sodium on the periodic table. So the reactivity increases as you go down the group. Same thing happens to magnesium and calcium. In fact, if you take a look at magnesium and throw magnesium into water, it really does nothing. But if you throw calcium into water, you'll see it reacts vigorously in front of your eyes. So the reactivity increases going down a group. There are some nice videos you can check online to see the reactivity of these elements. Right, let's take a look at group 17. And this group is called the halogens. These are also extremely reactive, kind of like group 1, extremely reactive. And they are nonmetals, because we're on the right side of the periodic table with group 17. Now, why are they extremely reactive? And the reason for this is because they are close to the noble gases, because they are close to the noble gases. In fact, if you take a look at these elements, here is the periodic table. The noble gases sit all the way at the end. These are noble gases. Group 17, which are the halogens, actually sit right here, right next to them. This is group 17. Now, group 1, which we also said were very reactive, actually sits to the right of the noble gases. So group 17 and group 1 flank the noble gases, and that's why these two groups are the most reactive groups on the periodic table. The reason to think of group 1, so if you think of the element sodium, which is number 11, it comes right after the element neon, which is number 10. Oops, I'm sorry, this would be number 10. And then to the right of it would be sodium, which is number 11. That's why sodium really fits right here, to the right of neon. So group 1 and group 17 are on either side of the noble gases, and that's why they are extremely reactive. When these elements react, they form a -1 ion, the halogens. And here you see bromine, this is the element bromine, number 35, reacting vigorously and producing a very, very bright light and fumes and so forth, extremely reactive bromine. Here they are, the 5 halogens. Here is fluorine. Fluorine is like a darkish gas, darkish brown gas. Chlorine, famously, is a green gas. Bromine is a liquid, red liquid. And iodine is actually a solid. This is iodine. You see a lot of variation. Gas, liquid, solid. This is really the one group that has a lot of different colors and a lot of different states. Astatine is radioactive. We don't really know what it looks like. it's extremely rare, so we don't have enough of it to see if it's has a similar color, but this is radioactive. And not many people have dealt with astatine, and really there's no reason to deal with astatine since it's extremely radioactive. Now the reactivity of the halogens increases going up a group. So we saw that with the first group, the reactivity went, as you go down, it increased. With these guys, as you go up, it increases. So here you have fluorine is extremely reactive, the most reactive. Iodine, not as reactive. It is also pretty reactive, but not as reactive. Here we see fluorine in contact with charcoal. Now charcoal is a fuel, so this here is charcoal, and all you have to do is spray some fluorine, or have fluorine come into contact with this, and it instantly ignites, producing energy. So fluorine is extremely reactive. Right, let's actually finish with this. We're going to do this in the next video, video 7.